unit, real actually that thermal evaporator unit. So there actually you will be knowing actually what is happening. So this gas transfer pump remove gas molecules from this pump volume and convey them to the ambient. So this is actually very simple. So gas transfer pump, what is doing? It's just taking away the molecule, means mostly the nitrogen and oxygen from the chamber and take it away. Okay. And convert them to that ambient. Okay. In one or more stage of compression. So there actually, like actually it will be running for a longer time. And so during running actually case that I will show you in gas transfer pump, how that actually there is a piston movement is there, and that is actually every stage, it's actually every rotation, there is a, you will get some sort of vacuum. So removal of the gas molecule means the vacuum. Now entrapment pump condense or chemically bind molecule on the surface. Okay. So it may be condense or maybe that chemically bind the molecule to the surface. Okay. So that is actually, just please keep in your mind, and this situated within the chamber. Now question is that this, we need both. Yes, because we need the gas transfer pump and also we need that entrapment pump. But gas transfer pump we should use first when chamber is just actually, I put that source as well as the substrate, close the chamber, all the vent is closed. Then first job is that turn on this gas transfer pump. Okay. So this, and so now actually this gas transfer, and last class actually I think I have shown one video. So there also you might be, I might remember that actually that how this works actually I explained. So the same line, so gas transfer pump, first you have to start and then the entrapment pump. When gas transfer pump will give sufficient vacuum, then only entrapment pump will be start, will, it will be started. So this entrapment pump that condense or chemically bind the molecule to the surface, and gas transfer pump remove gas permanently, and some of these entrapment pumps are reversible. Okay. Release the trapped or condensed gas back in the system upon warm up. So some pump actually their function is reversible, but in majority of the pump their work is irreversible. Once gas is going out, it will not bring the gas in. Okay. Now this gas transfer pump, again that can be subdivided into that two category. So here we can see that one is gas transfer pump, another is that entrapment pump. So gas transfer pump, that is actually positive displacement pump, rotary, mechanical and root pump. So rotary mechanical I will talk about, and then kinetic vacuum pump, so diffusion and turbomolecular pump, that two also I will talk about. So I'll talk about the rotary mechanical pump and I will talk about the diffusion and turbomolecular pump. So what is that overall classification? Means pump we can divide into gas transfer pump and entrapment pump. Then in gas transfer pump, it's actually work in a kind of irreversible process. It's just remove the gas molecule from the chamber. However, entrapment pump, what is do? It may condense or chemically bind the molecule to the surface. And gas transfer pump remove the gas permanently, and some of the entrapment pump are reversible. Now again the gas transfer pump we can divide into two category. So one is positive displacement, another is kinetic vacuum pump. So positive displacement example is the rotary mechanical pump. The rotary mechanical pump always can give you low vacuum, but if you want to give high vacuum, then kinetic vacuum pump, that is actually diffusion or turbomolecular pump. Okay, so that means in your chamber you need the combination of one positive displacement pump and one kinetic vacuum pump. And in some special application, you can use that entrapment pump. So this entrapment pump, that example is absorption, sputter ion, or cryogenic pump. That is actually some special pump, as I told. So I'm not going to talk in details, but I'll talk about little bit in details in brief, that rotary mechanical pump, diffusion and turbomolecular pump, because around the world, most of these thermal deposition unit, they use the rotary mechanical pump and the diffusion or turbomolecular pump. Now question is that where is the cryopump is being used? Cryopump is used for some sophisticated characterization unit, not in the deposition unit. So in this class, and another one thing, vacuum system is related into two sector. One is deposition, second is the characterization. So lot of high-end characterization, there actually you need the vacuum. So these two part actually we need to keep in our mind. So that's why last class I asked actually, do you know the XPS? In XPS actually we need very high vacuum. That analysis, that is actually called elemental analysis of material. Suppose you have a metal, you want to know that what is that elemental composition is there. So how you will do? Simple way that you can do the ACM, and along with ACM you can do this EDS. So energy dispersive, that spectroscopy. So EDS, from the EDS you can get what are the elements are there and their atomic percentage. Similar thing you can get in XPS. Okay. So photoemission spectroscopy. So these are called elemental analysis. So now actually the pressure range. So let's say that rough vacuum. So less than 1 millitorr. So less than 1 millitorr, in that range actually it can work. It will work. Up to this you can achieve. And rotary vane pump example, and they are actually in pump again. You should have two arrangement. One is pump, second is the gauge. If you do the vacuum, that is not sufficient. You have to measure what is your vacuum level. So that's why gauge is also important in vacuum system. So in this case, thermocouple, Pirani, capacitance, manometer, these are actually different gauge. That gauge can tell you what are the vacuum. Then medium vacuum range, 10 to the power minus 1 torr to 1 millitorr. So up to 1 millitorr, if you want, rough vacuum pump required, rough vacuum pump required. That is actually rough vacuum range, and the rotary vane pump can easily do this one. And then thermocouple, Pirani, capacitance, manometer, these are the gauge is being used. Second, in this medium vacuum range, cryopump, diffusion pump, turbomolecular pump, ion pump. Now why I put it red color? Because these are actually most widely used pump in that deposition unit. And in this case, that BA ion gauge, mass spectrometer, these are actually gauge is being used. But now when that vacuum level is increasing, you see sealing is important. These are called Vuitton seal. So this is actually now play the role. But in low vacuum, we didn't care. We didn't care. But then high to ultra high vacuum, 10 to the minus 10 torr to 10 to the minus 8 torr. In that range, this all metal seal is used, then baked system, and these are actually B ion gauge, mass spectrometer. This kind of gauge can be used, and the seal will be the metal seal. And what are that? Like turbomolecular pump, ion, titanium sublimation pump, cryopump. So here you can see that in this option, so previously like diffusion pump was there, but this is diffusion pump is not there. And a lot of new pump came. So that means if you want to get very high vacuum for some sophisticated characterization, you need some high-end pump. Okay, like ion pump, titanium sublimation pump, cryo pump, and these pumps are nothing but entrapment pump. But all this vacuum, in this range, if you want to operate, always actually it not necessary that you are This vacuum is required for your deposition purpose. This is required mostly for that some high-end characterization purpose like XPS or UPS. These are I gave just example, like sometimes you want to measure in liquid nitrogen or liquid hydrogen chamber, that you want to measure that current voltage measurement of a semiconductor. So how it's behaving at low temperature. So that kind of study, there actually this kind of like pump is being used. Now this is another one very important table: ultra high vacuum and raw vacuum. Okay, and at the bottom you can see that this is actually in torr. So if you want to operate in raw vacuum, you have only one option, that is actually in this, according to this table, that raw pump, roughing pump is actually you need it. Okay, and that's roughing pump up to 10 to the minus 3 torr. Then high vacuum range 10 to the minus 3 to minus 8. Here you can see that all range of pump is coming, like actually liquid nitrogen trap, then diffusion pump, turbo, then cryo. And this is actually just started, that ion pump and titanium sublimation pump. But this can be used easily in this range. But question is that when I can use with a low cost pump, why should we go for such a high cost pump? So that's why if you want high vacuum pump, the diffusion pump and the turbomolecular pump is that widely used. Then if you want high vacuum pump, then all entrapment pump will come, like cryo pump. Then you can see that this side actually it's actually these two titanium sublimation pump, ion pump, cryo pump, these are coming. Okay, so this is actually very important. I mean this one, and like actually this you should visualize in a, I mean on a in a chamber actually what is happening. So how that actually sequential step, and they are actually where we can use this raw vacuum as well as high vacuum pump. Now this vacuum system consists of one chamber, then one pump and one gauge. So you will need a closed chamber if you want to get a vacuum. So this chamber mostly glass or stainless steel and sealed with elastomer or metal gasket. Okay, so sealed with elastomer or metal gasket, and the pumps include mechanical, turbomolecular, diffusion ion, sublimation, cryogenic. These are actually different pump. And gauge like include thermocouple gauge for 1 to 10 to the minus 3 millibar, and this Baird Alpert called BA gauge. So BA gauge for 10 to the minus 3 to 10 to the minus 11 millibar. So that means you need two different pump for physical vapor deposition. One is actually roughing pump, another is actually like high vacuum pump such as turbomolecular pump or diffusion pump. And in both pump, low vacuum as well as high vacuum pump, you need two different gauge. So this is actually rotary displacement pump, and rotary displacement pump how it looks like, and this is inside the motor is there. It will rotate, and I have a schematic diagram, so there actually we can understand how it works. So rotary vane pump, how it works. So first actually you can see this is the piston movement. When in this is actually that in this situation, and this shaft actually it will actually move. Okay, rotating shaft, and this is actually you can see that how it's moving. So when it's moving, then this is just this passage is connected to the chamber. So whatever that, let's say at room temperature and atmospheric pressure, so whatever the pressure, then next stage you see that this is a confined area, and this area will be compressed, and here actually that this outlet will be closed. So what will happen, then this this whatever the trapped air, that in stage 3 the trapped air actually will come in this region. This chamber is closed, and now what will happen? With further rotation, there a pressure buildup will be there, and it will go out. So pressure will flow from a high pressure to low pressure region. So you just think inside initially atmosphere, then slowly it will goes down. So you have to pump out this molecule from there itself. So the what is happening? So here, then this particular pressure will be when higher than this atmosphere, it will go immediately. This means vent will open and it will go out. So this will several rotation. So first rotation maybe it will be easier to remove because inside will be 1 atmosphere, but slowly when inside chamber vacuum will be less than 1 atmosphere, then what will happen? That this action initially whatever it's ejecting, slowly that ejection rate will be less. Like actually it will eject less amount of molecule because inside actually vacuum generation is there, but due to this movement that inside you will get a vacuum. So this portion is clear, or if you have a question, please do ask that how the rotary pump work. Please do ask. And this is actually like a friendly discussion mode. So if you have any questions and you are in all are in final year, and I mean next year, I'm sure that you have to face, I mean in a company or in higher studies, some of the unit. So you should have a knowledge about this vacuum system. So at least the pump anywhere you need to operate. If you know that what is there in the pump, how it operates, so it will be easier for you. So the same thing actually explained here. So I'll put it, and I request you to go through, and just once again actually I'm explaining the mechanism. So initially that yeah. So initially what happened? This you can see that there is a piston movement, and this one in this position, and this inside this is actually connected to that inside chamber. So whatever the chamber pressure, here will be the same pressure. Then what will happen in stage 2, when it will move, then whatever trapped air will be disconnected with the chamber, and further actually in stage 3 it is going to the compression stage. So first is actually induction. So some of the inside chamber gaseous material or air will come here, induction. Second stage is called isolation. So here you can see that this is actually isolated from the chamber. Third is the compression. So when it further rotate, what will happen? Then actually this one rotate, and then this is actually closed, the vent is closed. So the not vent, this is valve, so valve is closed. So here this will be actually compressed, and when compressed it will be just slightly higher than atmosphere. This valve will open and it will go. So now this is the photo of this roughing pump, and the roughing pump from atmosphere down to this rough vacuum 1 into 10 to the minus 3 torr up to we can get it. And this is necessary that because diffusion or turbo pump have trouble starting from atmosphere pressure. So you can't start diffusion or turbomolecular pump from atmosphere. So you have to have one roughing pump, and that roughing pump actually basically will give you sufficient that vacuum, and then only that you should start that turbomolecular pump or diffusion pump. And usually the rotary vane pump can have oil or oil free. So this oil actually with oil, this is actually a little bit older technology, and say another latest technology is oil free. So in oil free pump, you need not to put that oil on a time basis. Like actually when you will see that like oil based rotary pump, that your pump efficiency, because let's say that you know that in your chamber in half an hour or 40 minutes, if you do the roughing for 30 minutes, you will get this vacuum like 1 into 10 to the minus 3. But when it takes 2 hours, so that means the pump efficiency goes down. So then actually you need to put the oil in that oil free, means in like oil rotary vent pump case. So and this problem, like actually you have to put the oil. So now in latest technology, it's become oil free. And this is as I explained that actually what are the different region of this rotary mechanical pump. As you see, this is actually rotating vane. And here, as I told, that there is a valve is there, and this is the rotor is movement. And here you can see that these oils are there, and this is actually this with this rotation we are getting the vacuum, and this inlet port, it will be connected to the chamber inside, and with the rotation of this rotating vane, basically that we are getting the vacuum. Now second is the diffusion pump. So this is diffusion pump is actually this kinetic, this one kinematic, sorry, this kinetic vacuum pump. So there are two things, positive displacement and kinetic vacuum pump. So diffusion pump and turbomolecular pump, these are kinetic vacuum pump. So in diffusion pump, what is happening? So inside there is a oil is there called diffusion, diffusion pump oil. So this pump actually will boil. With this is actually one boiler or heater is there, and this is actually oil pump, and this it will boil. So what will happen? This oil actually will go up, and some water cooling arrangement is there. This is actually water cooling pump, cooling coil is there. And when this boiled, I mean vaporized, that oil molecule will go up. Then what will happen? That immediately with this cooling action, it will actually condense, and then it will again, that after condense it will come down, and while actually coming down, it will adhere this like this gas molecule will adhere on this, it will on that liquid, and it's coming together. And this is, you can see that there is actually exhaust. So in that exhaust, no, this is actually an air molecule, not oil molecule. So oil actually will be condensed, and this condensed oil will liquidify, and that time it will, this air means nitrogen and oxygen will be absorbed there, and it will come. And here you can see that in this there is a particular pump is there, so it will not allow to go this oil outside, and only this air will go outside. So gas molecule will go outside, and this is actually heavy, viscosity is high. So that's why that whatever the liquidify, so it is actually, you can see that due to the positioning, it will not go out. So only that gas will go out. Okay. So this is actually, I mean, there will be continuous evaporation and condensation of this oil, that oil molecule, and those oil molecule will adhere on this particular gas molecule, and it will come and do that suction. This is actually how it looks like. And in this diffusion pump, problem is that that bottom there is a heater, so you have to be very carefully handle that heater should not be overheat, or there should not be coil burning or these things. Like I remember actually once, I mean, we started this diffusion pump, and we didn't pay at the attention. There was some problem, and then after some times, actually, this coil burn, and the diffusion pump stopped working. Then when we opened the chamber, and we realized that actually this basically that whatever the heater coil is there, that is actually there is some break, like in our normal heater also, if coil break, it will not work, the same thing. So this problem is there. And also that another one thing you have to keep in your mind, before starting that diffusion pump, you have to start that water cooling arrangement. If you forget to run the water cooling arrangement, what will happen? That here heating will be more and more, and finally actually the system may collapse. So this is another one part, that cooling arrangement you have to pay attention. Here you can see that outside this is actually cooling arrangement, the cooling line. This is that cooling pipe is there. Okay. And this is actually the heater, and this is the exhaust, and wherever through the heater gas the oil actually will evaporate, and here this it will condense in this region. So diffusion pump use a high speed jet or that vapor to direct that gas molecule in the pump throw down into the bottom of this pump, and this out that exhaust. Okay. And most modern diffusion pumps are silicon oil as this working fluid. That high speed jet is generated by boiling the fluid and directing the vapor through a jet assembly. Okay, and note that oil is gaseous. When entering the nozzle, within the nozzle, the flow change from this lamellar to supersonic or this molecular, and this often the several jets are used in series to enhance this pumping action. Okay, so these things actually already I explained, like diffusion pump has no moving part and are quite durable and reliable, and they can function over pressure range from 10 to the power minus 12 to 10 to the minus 2 milliwatt. And the oil of a diffusion pump cannot be exposed to the atmosphere when it's hot. If this occurs, then oil will burn and have to replace. So because this chamber is a closed chamber, so never this oil will expose to air. Okay, if it's exposed to air, then immediately it will burn. Now this is actually that, I guess this is yeah, the last part, turbomolecular pump. Yeah, in turbomolecular pump, yeah. In turbomolecular pump, this is actually how it looks like, and you can see the blade arrangement. This is one is called stator, another is called rotor. So stator and rotor in such a manner that when it will run in a very high speed, molecule will knock the wall like ping pong ball, and then it will basically goes. So turbomolecular pump, the gas molecule gain momentum in a desired direction by repeated collision with a moving solid surface. So gas molecule randomly will have a collision on the surface, and that is the starting point. And in a turbo, a spinning turbine rotor with angle bladed hit the gas molecule from this inlet of the pump towards the exhaust in order to create the vacuum. So this will run in a high speed, and gas molecules sometimes it when it will hit, then immediately that it will be trapped there. And this turbo, this employs the multiple stage consisting of rotor stator pair mounted in a series where the gas molecule captured by the upper stage is pushed in this lower stage and subsequently compressed to the level of this forward backing pressure. So what does it mean? Like this will rotate, and as I told, the gas molecule will heat and slowly it will go there. Next class, I'll try to show you at least one video of a particular this system so that you can understand. So turbomolecular pump, so you just keep in your mind the turbomolecular pump, this is actually rotating will be very fast. I think the rotation here, typically that 833 hertz. Okay, this kind of high speed is required, and then during the rotation what will happen, that gas molecule will hit on the blade, and this blade arrangement in such a manner, one it will heat, and then knocking by the blade, it will go inside that pump. It will not go outside. So that is that arrangement is being made. So atmospheric pressure, that mean free path of air is around 17 nanometer, but turbo blade cannot be built with a smaller clearance. So never expose directly to that atmosphere. So you should not expose the turbomolecular pump to that atmosphere. So first, you should get sufficient vacuum by roughing pump, and then only this turbomolecular pump will start operating. And this turbomolecular pump, like gas molecule, interact with the spinning blade and are preferentially forced down. So gas, how the blade arrangement is there. So if it hits, then actually it will be forced down. Okay. And this high vacuum required rotation of 20,000 to 90,000 revolutions per minute. So such a high speed rotation is required, and then 10 to the minus 3 to 10 to the minus 7 torque actually in that range is actually being made and ineffective before gas is in molecular flow. So using this rotary pump, you have to make sure that inside that chamber there is actually molecular flow is there, you can achieve, and then only you should start. So these are actually turbomolecular pumps and bearing, ceramics or magnetic, rotor option, the blade configuration that is important, and cooling air or water, because due to the high speed, of course, there will be a heating will be more and more. You should have a cooling arrangement in this case also. Okay, so with these things, actually, I just finish it. This another one. Next class I'll show some video and I'll talk about this cryo pump and where this cryo pump is being used. So if you have any questions, please do ask. Otherwise, I'll take the attendance. Just a minute. So any questions so far? Please do ask.
So,
Yeah.
so what is a four vacuum pump?
Which one? What is?
Four vacuum.
Which vacuum pump?
It was towards the it was under turbomolecular pump.
It was under turbomolecular pump. Yeah. Yeah. Which one? Now.
The last line, sir.
Oh, okay,
The
okay, okay,
four vacuum
okay.
pressure.
Yeah, yeah. Actually, this turbo employs the multiple stage consisting of rotor and stator pair. Okay, mounted in a series. Okay, that is actually up to this. So there is actually rotor or stator. So one layer we call rotor, and then another arrangement we call stator. So this is actually paired. This will be paired in a pair and several pair mounted in a series where the gas captured by this upper stage is pushed into that lower stages, and this where the gas captured by upper stage, it will be captured by the upper stage and is pushed into the lower stage. So gas will be captured on the top surface and then it will be slowly pushed down. How it pushed down? like first it will hitting, like if you hit by using a bat on a ball. So similar, like this blade will hit, and when it will hit, that you can see that this arrangement in such a manner, it will hit to the below only, and then it will come down. Okay, it pushed into the lower stage and successively compressed to the level of this 4 vacuum pressure. Okay, so this is actually a 4 vacuum pressure, like actually backing pump. So it compressed to the level. So actually this is basically that it will compress, and it will basically that it will make it out. Okay, like that, compressed to the level of that 4 vacuum pressure. Okay, that's all. So basically that is nothing but it's not a like uh, it's a backing pump, like it will compress and then it will just removed from the chamber. That's all. Two different pump has a two operation is totally different. Once again I am explaining the diffusion pump, how it operates. You have a diffusion oil, you need to burn the diffusion oil, sorry, you need to evaporate the diffusion oil by you need to boil the diffusion oil, it will evaporate, then due to the cooling action it will condense, and while condensing it will contaminate it with the gas molecule, and it will take the gas molecule with the condensation, and then it will come to the exhauster side and it will come out. And several times that this evaporation and condensation is happening for this diffusion oil, diffusion pump oil. That is the function. In turbomolecular pump, there is no pump, or here only that stator and rotor. So stator and rotor will move in a high speed, and it will hit like a ping pong ball, and then it will, that ball actually will come inside, and finally that at the below that pressure, some pressure will build up and it will go up. But this is that principle of the turbomolecular pump. Yeah, any other questions? Any other questions? Please do ask, otherwise is it okay? Who asked? Actually I forgot.
Yes, sir, it's fine.
Okay, because this is actually next class I'll try to show you some animation. There actually this part will be, you will get much clarity, better clarity. Okay, okay then. Okay, bye.
Thank you, sir.
Sir, any information regarding quiz? Left.